So we're in the business of connected device management, and the connected device market is fairly big today, but it's I think it's on the verge of an explosion and a transformation. What we've seen so far is essentially stovepipe type connected devices, either your mobile phones that are managed by operators, and it's a pretty closed system, or even your Android or iPhones. I would say that they are reasonably closed ecosystems as well. If you want to program it, use those as a device for your application, you kind of have to buy into their entire culture, and they will also have a lot of requirements on your code to even allow it to run on their devices. We are betting that what the market will want, and we're trying to tell the market that this is what they want, is a more open system, a system that's more friendly to entrepreneurs. Because nowadays you can buy a fairly capable small device for a few hundred, not even a few $100, like less than that. You probably, many of you have a Raspberry Pi lying there at home somewhere, gathering dust. How many of you have actually used your Raspberry Pi? Okay, a few. How many of you haven't yet? About as many. I have one too. I haven't unpacked it yet because I let my colleagues do that, and I program the server side. So we want to provide connected device management as a service. And we try to visualize it like this, where our stuff is the blue stuff in the middle. We have a server side that does device and traffic management. We do provide device components, open source software for device programming. But essentially, you do the device programming and you do the back-end logic, typical web server. The interface here that we provide for now is JSON RPC. And the interface on this side, at least if we get to choose, is BERT RPC, which is an Erlang-style RPC format. But at least one of our customers is actually using their proprietary protocol with devices that they have written in C++. And we provide a plugin then in our server. So some of the challenges briefly about device management, connected device management. One is coverage. If you have devices that are actually going to be out in the field, you can't really depend on the communication or the connectivity there being that good. This is Sweden, 2013. Sweden is one of the countries with some of the best mobile coverage in the world. This is SMS coverage. A little bit bad up here. This is 3G coverage. You can see that in half the country, there aren't that many people living there, but in this half of the country, you really don't have much 3G at all. And 4G, well, that's not much. Unless you're in the big cities, you don't have 4G. I have almost 4G. I have a 4G modem that I'm running 3G on because I can't really get a lock on the signal at my house. So looking at the US, this is the results from a survey of what kind of download throughput you have at different measurement sites. And you can see that in most cases here, you have less than 768 kilobits. So the normal case in many places, especially if we talk geographically, is that you have very poor coverage. And if you're going to make a device management service, you have to be aware of this. And you have to be flexible. You really have to also know about the rate plans. If a device happens to be roaming, you don't want to push firmware upgrades to it. Your customer is probably going to switch to a different provider then. So what our server does is it's essentially a store and forward system. You could look at it as a request router between your backend logic and the devices. And it keeps track of when the devices are online and what kind of connectivity they have. If they're not online, we will queue the RPCs. And if you have push notifications enabled, we may push an SMS to the device, letting it know that there is stuff to be fetched from the server so that the device can connect when it's convenient. Now, in our model, it's always the device that connects. We don't want to actively connect to the devices unless we have to. So we also support scheduling operations in time. So if you want to do firmware upgrades of a lot of different devices, you may actually want to, like for example, Apple does, and that once they have a firmware upgrade, it may be a while before your phone is actually scheduled for upgrade. So this is fairly standard stuff. It's the kind of stuff that you don't want to do yourself. If you have a great idea for a new smart connected device, you don't want to spend most of your time building a management system that keeps track of it and does the upgrades. And you don't want to spend the majority of your time plowing through legacy device management protocols. That is not fun. So one thing that and that's what I want to try to illustrate today, is sort of the lead time challenge. If you have a great idea and you can buy the device, or you got your Raspberry Pi handed to you at some conference and you want to go home and you want to play, it's loaded with Linux. You know how to program that. And you can buy some connectivity stuff for it, and you can have a lot of fun. What we want to support is to allow you to go from a great idea to an end-to-end working prototype that you can show potential investors, preferably within a week, if you're a smart guy and very motivated. So we try to be not bloated, and we also try to not be too limited. This is the challenge, to allow you to very quickly get started, but not to cover all the functionality that we can provide within a week. You want lifecycle management. Let's see. So we haven't really, we do have a free server up and running for the Linux Automotive Foundation, people who are members there. But the plan we have is that you get the first 10 devices for free, so that you can do experimentation and demos to impress people with your idea. And then there will be a progressive licensing scheme once you field this commercially. And some of the features, more complex features that we have, are really intended to allow you to evolve your devices so that you can have multiple generations out in the field and still be structured in how you manage those. So, and this is the programming by contract part. We have a specification repository in the server. And so what you do is you specify your RPCs, the APIs, and the notifications that come from the devices in a fairly nice looking specification language. You tie that to different devices, and the system will then validate all incoming and outgoing messages against the schema you provided. And the specification language is Yang. It's actually an evolution from XML or SNMP, XML RPC, various other technologies. So if you've heard of the standard netconf for network management, this is the modeling language for netconf. And it's about as nice as they come. And we would like to push that as a more general way of specifying APIs. Some of the customers we have that are in commercial service right now is a peer-to-peer car sharing company in San Francisco, where the idea is if you have a car that you're not using during the day, you can register it with their service, and they have something they call the car kit that they install in your vehicle. So when someone wants to rent a car, they go to their service, they check which cars are available in the vicinity, and they can choose which kind of car, how much they want to pay, fancier cars, higher rates, and so on. And they go to the car, they identify themselves with the iPhone, and the service GetAround can remotely unlock your car so they can get in and drive away. So you don't have to be there. And they monitor where the car is with waypoint tracking, and they have a kill switch, so if someone tries to run away with your car, they can actually stop them from doing that. So that's these are the guys that have a device coded in C++ and a proprietary protocol. Another system that we support is a little fingerprint scanner that actually one of our founding partners designed and manufactured for the customer, where patients can identify themselves with a fingerprint and some other authentication, and that ties back into the information repository on the server so that doctors can get their medical records and things like that. So the thing I'm going to talk about today is we had this demo with Jaguar Land Rover, and that is one of their chief engineers, Matt Jones, who was talking at the Linux Foundation Collaboration Summit. And the idea was to very quickly come up with a prototype of some kind of connected car application. The entire car industry is trying to figure out how to make cars connected and interesting so that you as a driver get a good experience. Their problem is that if they ask people, what do you want in your car in terms of connected experience, nobody really knows. It's essentially they will know it when they see it. And typically they will probably know what they don't want when they see it. So this was a way to try to stimulate some prototyping for the car industry. So what we did was to remote control the air conditioner in the car. I don't know how useful that is, but essentially we had an iPhone app and a web app, and you had the touchscreen in the vehicle, where another company programmed the web interface using WebKit. And that application talked to our device software that talked to our server, which forwarded information to the web server and also the iPhone. So you could control it from your iPhone and from the website and from the car. This was a 3-week project. And this is the reference hardware that they use in the automotive sector. It's not an extremely impressive CPU or anything. So I would say the main thing about it is that it's very rugged and it has the interfaces that you need to hook up to the car. So it's not the kind of hardware that you would probably buy. So here is a schematic of the application. So the CAN is a controller area network. That's a kind of network that you often find in your heat pumps and stuff like that at home, also in cars and in a lot of different machines. It's a fairly nice low latency network. So our Exosense device uses our CAN protocol stack to talk to the network bus and the climate system. And then we have this application that I'm going to walk through. And the web app, the WebKit app, used JSON RPC to talk to a little web server in our device software. And then we used went through our little proxy application called Exoport that talks to the server, which in its turn talks to the backend web app using JSON RPC. Sounds a bit complicated, but I guess the complication for you is how much code you would have to write. This would be the basic steps. And it really didn't take many days to do this on our side. You create an account on the server. That's well, simple registration. You write your Yang spec. There is a nice little Python program called Pyang that will parse it and validate it and tell you that it's syntactically correct. You store that using, for example, a curl command that we provide. Then you go in and you define your device type and you link that to the Yang specification. And then you start defining devices and give them this device type. And then you just write some device code and demo, and then you get lots of money. Actually, we didn't get paid 1 cent for this particular demo, but theoretically, you get lots of money. So, the specification, this is Yang. You create a module, you give it a name, basic namespace stuff. We have a specification called Exosense that you can import, and that gives you access to some basic types and request parameters. And this specification will then be used in this validation loop, where anything that doesn't conform to the specification will be rejected. The requests that actually do conform to the specification will be converted to or normalized. So you deal with the structures that the validator spits out. And then that's forwarded to the device. So an RPC specified in Yang, here we're going to look at the set fan speed request RPC. So it has an input section, an output section, and in this case, this is a standard. Here, you inherit the standard request parameters that we have provided that tell the server what device it is, and there are some other parameters you can set optionally, like request timeout and things like that. And these are the standard reply attributes. So here you don't really, this is just boilerplate. This is the stuff that isn't boilerplate. The fan speed attribute, which is here an unsigned 32-bit integer. So that was your specification for this particular request. Now, if you would want to test this, what we normally do, we write a curl script, sort of copy and paste. You put the JSON here. So this is just a standard JSON RPC. You call the JLR demo :set fan speed request, and here you provide the device ID and the fan speed that you want to set. So far, fairly simple. Now we get into the actual code. And this is Erlang code. How many of you have ever programmed in Erlang here? Well, a few. So the rest of you are going to be experts after this. So the entry point here, let's see, this is from the local web server. So that was from the WebKit application. So, and that request is also validated, but on the device side. On the device side, we actually take the Yang spec and compile it to Erlang code because we have less CPU power there and fewer specifications to worry about. So we just check what the method was. And here it's set fan speed request. And what we do here is we call this is just the helper function down here, where we pick out the fan speed argument and we send that to the can library to create. We're going to look at that later. What we also do is we forward this upstream. We do an export RPC and we just forward that request up to the server, which is going to forward it to the web server on the back end. And this is the entry point when the RPC comes downstream from the server. And we call the same helper function here. And then we send it to the HTTP via the HTTP client to the WebKit application running on the panel in the car. So essentially, it's just sort of a two-way switch here, or three-way. It's also talking to the CAN bus. The CAN bus code, this is almost all of it that pertains to this particular request. Here's the start function, and you start the CAN router, and this is actually the initialization code for this, where we tell it to start the CAN protocol. We just start the socket server, and then we send an initial CAN frame, and then we set a refresh timer. Here is the code that is needed to set the fan speed. We extract an offset and a length for the fan speed part of the CAN frame. And here we have the packet, which was the initial CAN frame from the beginning, and then it can be updated later. And we just pick out what comes before the fan speed attribute and what comes after. This is Erlang bit syntax, which is pattern matching on an octet string. And then we put in the speed here with the length indicator. Or the length indicator just tells the compiler how many bytes to insert here. And then we send that packet. And we're done. So that was actually that was it. That was the only difference there. So not a whole lot of code. And of course the main change here from the past is that these devices are actually real CPUs. They're about as powerful as your desktop was some years ago. So they're running Linux, running something like Erlang. Actually, Erlang has a smaller footprint than Java. So if you have, well, say you have 128 megabytes of RAM, which is nothing, then you can run very comfortably. 64 megabytes of RAM, it depends a little bit on what you're doing, but for most device side applications, it's not a problem at all to do this within 64 megabytes of RAM. And of course the advantage is you can do this very quickly. It's not that much code. Provided you have nice libraries. So I'll list some of the libraries that we have built so far, and these are all open source. These are the ones we have released so far as open source. We're a little bit unstructured in our release process, so this may have passed you by, most likely, even if you were looking for them. We have an SMS library that allows you to, for example, subscribe to messages from a certain phone number or whatever. You can pattern match on the actual content of the SMS so that you can get sort of content-specific subscriptions. Only give me an SMS where the text is prefixed in a certain way. We've been running RPC over SMS using this, which is a bit perverse perhaps, but it does work. We have a netlink library. So netlink, I don't know how many of you know that, but that's basically the subsystem that keeps track of the different communication protocols that you have in Linux. So this will notify you when, for example, the Wi-Fi comes online. PPP and SMS data multiplexing, that Exoport, which is the proxy application that connects to our server. A fairly nice and pretty speedy gpio library. For example, if you want to, this is sort of low-level communication. If you want to control diodes and stuff like that, or pretty much any types of physical interfaces, you can do that there. An input device management library, a GPS manager so that you can collect GPS data, and also a database management system. This is the same database management system that we use on the server. And what we feel is fairly nice with it is that it handles tree-structured data. So if you want to deal with and traverse configuration data, this is a very handy way of doing it. It also has support for the queuing and dispatch needed for Exoport. So it's the same thing there. If you're on the device side and you want to issue an RPC to the server and you don't have coverage, it will be queued by Exoport and dispatched once you're online. So some of the things we're working on, EPX is actually a frame buffer graphics library with support for 3D and animations to make nice touchscreen graphics on your device. We're also working on the sort of prioritization component that will be rate sensitive and try to make sure to always use the most efficient and most economical connection if there are more to choose from. And also make sure that you don't send stuff that would be too expensive or unnecessary if you happen to be on an expensive link. And also a configuration manager, a little bit more extended than we have today, and a package manager. We've gone through a number of iterations here. It would have been nice to just pick one of the ones out there, but I think we've realized that we're going to have to support a number of different package managers and then provide an abstraction on top that works with our system. And also support for chunked file transfer between server and client. So for example, if you want to send a big firmware update and you lose coverage in the middle, you want to be able to pick up where you left off. I'll show you some more code examples. This is sending an SMS. You basically just provide the number and the text. Fairly simple. Receiving the SMS, you can subscribe to a certain number, and then this flush, this is just because we're in the Erlang shell, and this is the way to tell the Erlang shell to present the messages that have come into the shell process's mailbox. So now it's actually the shell that's subscribing to these. And you get a fairly detailed message. Now you would use the record syntax in Erlang to select data from this, but it does provide you with a lot of metadata. So here's an example, a one-slide version of how you could do a remote unlock of a car door, for example. And this is actually all the code. So here's the start function. You start the UART, you start the SMS subsystem, you start the PPP manager and the CAN router. And then you just spawn a process that subscribes to SMS messages, and you are in a loop. Here you receive an SMS. A bit simplistic, but this is slideware, although working slideware. An unlock request, you compose a CAN frame. This was for a little demo campus vehicle that our partners had built. You compose the CAN frame that matches whatever unlocks the car. This is not standardized, so it would be specific to your certain device. And you send that message, and supposedly the car door will unlock. So device programming nowadays can be pretty high level and actually pretty comfortable. And you can do some pretty awesome stuff in just a few days, and with fairly small amount of code. So, and this is sort of the altruistic part. We feel that if we want to do this, there is sort of the boring side of device management where you try to go for those who have a lot of money. We want to go for the people who don't have any money, which seems like a lousy business plan, but it's more fun. Actually try to provide something to the community and the open source users so that there is sort of an entrepreneur, hacker-friendly way to get into connected devices and do rapid prototyping end to end. That was pretty much it. Do you have any questions? Yes?
Where did you get the car matrix for your car stack from? CAN stack from?
For the, which one? I'm asking your iPhone.
Maybe you can read.
So the actual specification for that came from the vendor, obviously. So we had to cooperate with them. So they told us basically what the CAN frames would look like, and we just formatted them. So, like I said, there is no standard for that. So what we provide is a library to be flexible about how to do this. We also have full CAN open support, and CAN open is a fairly ambitious framework for sort of industrial CAN applications. Question is how many are actually using that in practice? I don't really know. But there is a lot of hype about CAN open. And so if you need CAN open, we do have CAN open support.
What about security?
On the JSON RPC side, it's HTTPS. We try to use best practices for password handling and things like that. We do support various authentication methods. Basically any ones that the YAWS web server supports, which is just about all the standard authentication methods. On the server to device side, we use BERT RPC over SSL. For example, the car sharing company, they have their own secure protocol, which they take responsibility for, and they have designed. And we just provide the plugin. And the system on the server side is sandboxed. When you get your account, you can create users, and per user, you can specify which resources they have access to. So it's essentially a role-based access control protocol where you can define this, or rather it's fairly statically defined right now, but it's going to be become more flexible. like all these things, it's not so hard to implement. It's a user interface issue. That's the tricky part. Making it user-friendly is harder than actually making it work. So it works. It's not necessarily user-friendly, but it works. So in that particular case, we actually did introduce optional semantics for whether you want to do store and forward or not. So the default was to have store and forward, but obviously when you do the typical maintenance commands, they're not queued in the server because they're actually handled directly by the server. And so we do have a mode where if the device is online, we don't go through the persistent queue, we just dispatch it directly. So in that case, what we do is dispatch it directly. There is no point in storing it and then serving the request a week later. So, and that's actually optional per request or per specification, however you want to do it. Okay? Then I thank you.